The two graphs you see in front of you are meant to represent the concept of inverse functions. And of course, based on these two graphs only, it's kind of difficult to figure out what that concept is, isn't it? Well, yes, these two curves seem to be somewhat similar to each other in some way, but we need to figure out a little bit more in depth what that is. Well, let's look at the graph on the left side, and let's figure out what happens to the function when the initial value, the input x, is equal to 2. Well, in order to figure out what happens to x equal 2, we need to go up until we hit the graph, and then to the left until we hit the y-axis, and that gives us a y value of 4. Now let's take that same value of 4 and use it now as the input on the right hand side. So we do the same process. We start from x equal 4, go up to the function, left to the y-axis, and we end up with a y equal 2. So it looks like these two functions, at least in this particular point, are reversing the input and the output. On the left hand side we started from 2, we arrived at 4. On the right hand side we started at 4, we arrived back at 2. Well, there are other similarities of the same kind. For instance, the left curve includes the point 0, 1. The right curve includes the point 1, 0. The left curve includes the point, the intercept negative 1/2, 0. The one on the right hand side includes the intercept 0, negative 1/2. So it looks like these two functions definitely have some kind of connection having to do with switching coordinates. And in fact, that is exactly what the connection is between a function and its inverse. And these are the notations that we're going to be arriving at eventually. But for now, we'll investigate a little bit more the key ideas behind inverse functions. So what is the key idea? Well, let me remind you of what a function is. A function is some kind of a process that takes a number and changes it into another. If we start with any number on the left hand side, well, this function will change it to a number on the right hand side. So we start from x and we construct f of x, which is some other number y. Well, the question we're going to be looking at right now is, can we go backwards? If I start from a value of y, can I retrace which value of x gave rise to that value of y? If I can do that for every possible y value, then that means I can construct a backwards function, which for now we'll call g, that provides for each value y the corresponding value of x, which would generate y under f. It looks complicated, but it's really all we're doing is we're trying to go backwards. So in fact, the relationship between the variables is the same. We're just associating to every x a y, to every y an x, and so on. It's just the role of the variable that changes. So we're in f we're using the x numbers as the input. In g we're trying to use the y values as input. Let me give some examples of where this occurs and can actually be useful. For instance, we have two major temperature scales that we use here in Canada, especially thanks to our cousins to the south. One is the Fahrenheit scale and the other one is the Celsius scale, right? And they're related by this equation. So if I give you any Celsius temperature C, which Environment Canada might give us, I can use this formula to figure out how to communicate that temperature to our American friends down south. Notice that in this relationship, C, the Celsius temperature, is the input, the starting value, while F is the output, what we get as a result of applying the formula. And of course, we can represent this relationship through a graph, which in this case, of course, is a straight line. Now, the question of inverse functions is, well, can we reverse this? Can we go in the opposite way? What if some American fellow wants to communicate Fahrenheit temperature to us in Celsius? So can we use F as the input and obtain C as the output? I'm sure that you know how to do that algebraically, but we're again looking at this as a relationship. So the new relationship that we would obtain will look something different, because this time we're going to have F as the input on the x-axis and C as the output. A couple of other quick examples with no formula, but just to emphasize the use of these inverse functions. Let's say that we have a moving object. Then we can figure out what the distance covered by this object is in terms of the speed, right? D is going to be equal to V times T. Well, can I reverse that? Can I obtain speed in terms of distance? Well, all you have to do is write down velocity as time divided by distance, and you get the reversal of the initial relationship. So notice it's exactly the same equation pretty much. The only difference is which quantity are we using as input, which quantity are we using as output, and in this case, of course, we are assuming that the time is constant. Another possible example, and of course there is millions of them, another one is planetary motion. Let's say that we have a way of figuring out how far the Earth is from the Sun in terms of time. So at any given time of the year, how far is the Earth from the Sun? Well, can we reverse that? Can we figure out, given the distance of the Earth from the Sun, what time of the year it is? So let's develop a little bit the notation for these inverse functions. So again, we're starting from a regular function given y equals f of x. Remember that what we're trying to do is we're going to try to go backwards. So what we want to do is we want to express x as a function of y. And of course, it's going to be a different function. But this is not really good notation because we want to maintain x as the letter representing the input and y as the letter representing the output in general abstract mathematical context. Of course, if we're doing applications, we want those letters to represent the quantity. But if we're talking about abstract mathematical things, we want to keep x as the input, y and as the output. And we also want to maintain some kind of a reference to the original function f. So the standard notation that mathematicians have devised is, well, you want x as a function of y, fine. So what we're going to do, or we want to go backwards, so what we're going to do is we're going to represent this new function, this new process that allows us to go from y back to x as y equal f inverse of x. But remember, in this new formula, y is what x used to be and x is what y used to be. Okay. So there is a switch in the x and y roles, and that's represented in the switch between the letters that we use for x and y. Now, make sure that you do not confuse this notation with the similar notation that we use for the reciprocal. Remember, the -1 power represents a reciprocal, but this -1 placed just near the name of the function f represents the inverse. So the reciprocal is written as f of x to the -1. And now that's a power, and that represents 1 over f of x. But that's a different thing. We're going to see in some examples later how they're different and how important it is not to confuse them. This switch that is this switch, which is the key characteristic, the key idea behind the concept of inverse functions, generates another very important property of inverse functions. So let's say that we start from a function y equals f of x, and we're looking for f inverse of x. Now, remember that every point on the graph of the original function is of the form x f of x, where f of x, of course, is going to be the y coordinate. On the other hand, every point on the graph of the inverse function is going to be of the form x f inverse of x, where again f inverse of x is going to be the y coordinate. But these two pairs of numbers are related. In fact, remember, the old f of x is actually what becomes now the new x, because f of x is y and we're switching x and y. We're switching the roles of the two variables. And similarly, the new f inverse of x is really what the original x was. So what we're doing in going from the original function to the inverse is, again, we're switching coordinates. So that means that if we draw the line y equals x, each point on the original function will end up becoming the point which is right across from it along the line y equals x, this diagonal line y equals x. So if we pick another point there and we're trying to figure out what that becomes in the inverse, will be something which is the mirror image of it on the other side of the line y equals x, and we can play the same game for any other point. And if we do that for the whole curve, we realize that in fact the inverse function has a graph which is actually the reflection around the line y equals x of the old function. And of course, once you're talking about reflection, we can talk about these two curves being reflections of each other around the line y equals x. Now, this is a very important concept, but it's also, especially at the beginning, a potentially confusing one. So I do recommend that you think about it and you don't just gloss over it, but maybe do some exercises or think about what I've just said and make sure that you convince yourself that this is true, and it's true even for other points that I did not show you, as well, of course, as being true for any other function.